speak about patterns in random permutation. This time we're going to take the pointer out to a different place. It's Hillel at 70 College Avenue. It's a self-service dairy restaurant. Everybody who wants to come is welcome, but you have to let me know right after the talk. It's 70 College Avenue.
Okay, thank you very much. Thank you for having me, and please feel free to stop me with a question at any moment. So I think that
Everybody just keep this fast, so we're going to 5:50.
Okay, very good. Okay, so I understand that you often mention here permutation patterns, so let me just repeat quickly the definition. So we will write permutation and we'll think about permutation in the one-line notation. So for example, here is a permutation pi in Sn, where n is equal to 5, then we'll write pi is equal to 3, 5, 2, 1. Or an ordering of the number between 1 and n, okay? And we'll think about n, which is large, and going to infinity. Okay, so this is a permutation. Now, a pattern of size k for every fixed k, and so we can restrict to k entries. So for example, let's take k equal to 3, and then sigma in Sk is a pattern. Here's the definition: a pattern that occurs in the permutation pi if in these 3 entries you find the ordering type of sigma. So sigma in this case will be 3, 1, 2. So this is the only permutation in Sk that preserves the ordering. So the largest goes to the largest, the second largest to the second largest, and so on. And they are listed according to the ordering which they occur. Okay, and today we'll think about k that is fixed. Okay. So when we have such a permutation, then we can look at all occurrences of patterns that we can find in it, and try to see how many do we have of each type. So for example, in this permutation, let's take one again, 3, 5, 2, 1, 4. We can see that it avoids the pattern 1, 2, 3 because it never because you can never find 3 entries that are ordered this way. But 2 let's take the same one, 3, 1, 2 occurs in pi actually twice. Okay, so you can find another occurrence of the same permutation, which is, I think, the 5, 1, 4. So it makes sense to ask how many times does each pattern of size k occur in a larger permutation of size n. So this motivates the following definition. How do I move?
No, they don't move.
They don't move. So you just...
At least not automatically. You have to down.
Okay.
Yeah, with the wrong order.
Okay.
That's the miracle I do this.
So you know about permutation patterns, and we are trying to count them. So let me make a definition of densities. The density of sigma in pi is, and we'll denote it by T, sigma pi is equal to the number of occurrences of sigma in pi divided by n choose k. Why n choose k? Because n choose k is the maximum. We have that's the number of k, the total number of k tuples in permutation of size a. And we also define a vector, say k profile of pi is the vector p k of pi, all pattern densities for every sigma. For sigma, we run over sigma in sk. So this vector lives in a k factorial dimensional space. Okay. So these are the definitions, and we can, for example, write the 3 profile of our permutation 3, 5, 2, 1, 4, and it's going to be a 6-dimensional vector, which turns out to be 0, 0.3, 0.1, 0.2, 0.2. Now we have to order the coordinates in some way, and it doesn't matter, so arbitrarily we're going to use the lexicographic order here. Okay, so at least for 3, let's make it explicit, we'll see it again. Okay, so these are pattern densities, and they're good for many things. So for example, there's many extremal questions in this area. How many permutations avoid a specific pattern, like here? So it leads to enumeration questions, it leads to extremal questions, like what's the maximum number of occurrences you can have of a specific pattern in a permutation. It leads to the definition of a limiting object for permutation. So you can ask, if you have a sequence of permutation for each n, do they have a limit? So a natural choice is to say that they have a limit if every density for every fixed pattern, the density of this pattern has a limit. This helps to define limiting object for permutation. In application, it's useful in property testing. So you can test for different properties you define of the permutation by looking at random places and see what the patterns that you see. And it also has some application to nonparametric statistics, and maybe I'll mention them later. Okay, but the question that we want to answer today is quite basic. Take a random permutation. What is the distribution of this vector? So for each density becomes a random variable for a random permutation, if pi is random, and the profile becomes a random vector. So let me give them names. So P sigma n is a random variable where pi from Sn is uniform. Okay, and Pkn is a random vector that we're going to call the random k profile of the permutation. So what's the random 3 profile of a random? So what's the 3 profile of a random permutation of size n? So let's start with some observations about this object. So what is the sum of all entries in this vector?
1.
1, yes. So let's write it down. The sum over all sigma n sk of p sigma n for every n, deterministically, for every k and every n is equal to 1. Let me even write it differently. The inner product of pkn and the all 1 vector is equal to 1. When the inner product here is a usual inner product, the the inner product of A and B, sum over A and BI. So that's and this means that the profile is actually restricted to a codimension 1 hyperplane in this space in out of the K factorial. Okay, so is it more restricted than that? That's a good question. Let's see some more facts about this random value. So what is the expected value of P sigma n? Let's say that sigma is in Sk. For any sigma in Sk, what is the expected value of its density?
Well, that won't depend on the permutation.
So there are two parameters here, K and N, or sigma and N, and indeed it doesn't depend on sigma. So then what would it be if it doesn't depend on sigma, and they add up to 1, and there are K factorial of them? So it's going to be 1 over K factorial. So there is some symmetry here. I mean, we look at all restrictions to K places and look at the resulting pattern, and it can be any of the K factorial patterns, and it turns out that on average we expect to see 1 over K factorial percentage of each one of them. Okay, so and indeed there is a symmetry because why there shouldn't be? I mean, we look at 3 fixed places in a random permutation. Their ordering can be any ordering with the same probability. Okay, so is it clear? So so we have this expected value for each one of the densities. So we can say that, but we can say even more that actually you can, and for this we need the variance. If we take Pkn, then it converges in probability to its expected value, which is 1 over K factorial, 1 over K factorial, vector this point in space. K factorial entries, each one of them is 1 over K factorial. Okay, so a conversion in probability means that for every open neighborhood of this point, the probability that the profile of the permutation falls in this open neighborhood, open ball, goes to 1 as the parameter n, the length of the permutation, goes to infinity. And this follows from variance consideration. So for this you only need to know that the variance of P sigma n is O of 1 over big O of 1 over n. Okay, is it clear? So this raises more questions. So we know that as n grows large, we know that we expect to find the random profile closer and closer to this point. So we can ask, okay, so how does the difference, the deviation of the profile from that point, how does it behave? What kind of fluctuations do we expect to see from this point? And let me mention some results about this distribution. So in 2010, Alex Burstein they gave formulas that I'm not going to repeat now, but they gave a formula for let's call it sigma of sigma and sigma prime, which is the limit as n goes to infinity of the covariance between square root n p sigma and square root n p sigma prime n. So you take two densities of different patterns, and you ask what is the covariance between them. So the variance here is a special case when you take the same sigma twice. And and you have well, you know that everything goes to 0, but you have to normalize by multiplying by square root of n those density, and then it converges to some numbers, and they get formulas that give you these numbers depending on sigma and sigma prime, so that you can compute them. And in particular for the variance, it's some constant that is non-zero. Okay. And then another result in 2015 by Janson, Nakamura, and Zeilberger is that you actually can say something about the all joint distribution. So you multiply by square root of n the difference between the random profile and its expected value. So let's call it UK. Let's define this point in space to be UK. So the difference between them converges in distribution as n goes to infinity to some multinormal random variable. So you can write it as n0 and this metric of sigmas from before, where here you run over all sigma and sigma prime of size k. And let me write it, sigma in sk, sigma prime in sk. Okay, but the interesting point is that this multinormal random variable is actually supported on a lower dimensional space. So it is supported on a k minus 1 squared dimensional subspace. Okay, so the limiting distribution is degenerate and supported on a much lower space. So we started with k factorial, and then we went down to k factorial minus 1 because of this linear deterministic restriction. But when you go to the limit, it gets closer and closer to a subspace of this much smaller dimension, k minus 1 squared. So this leaves some questions. So we know that its order of the fluctuations are order of 1 over square root of n in this space, which means that there's little o of 1, there's smaller order in the orthogonal complement. So this raises the question, how small are they, and in what direction are they? Do they have what order of magnitude? And it also raises the question, why is it interesting to look at them? After all, they are so smaller order, maybe they are not important. So we'll see that they are important sometimes, and and we'll see how small they are and at what directions. Okay, so that's our goal here today. Okay, any questions so far? Okay, everything clear? Okay, or should I continue? I mean, should I spread to all?
Yeah, but here then.
Here.
Don't let anybody here who can lift that backboard.
Okay, I'll try. Okay, so let me tell you about this. More about this distribution. So
So you can say more about it than all the time.
We're going to say more about it. So I don't want to cover this part. So I'll use this one. So I'm going to use some decomposition of the k factorial dimensional space. And at first I'm not going to define it for you, so I'll just say that it exists, and later we'll see its definition. So first I'm going just to say there exists a decomposition of the k factorial dimensional space into k is a direct sum of k components, like that. And for every sublet, so this decomposition is, we'll determine in a moment, for every r, okay, and vector in the r's component of the space, a non-zero vector, we project the random profile along this direction. So we are doing it by taking, we take the scalar product and the inner product of this random variable on this fixed direction. So this gives us some random variable. So we start with it's a combination, it's a linear combination of this k factorial random variable, which is another random variable. And we want to say something about its order of magnitude on average. So we square it and take the expected value. And the claim is that as n goes to infinity, this is asymptotically equivalent to some constant over n to the r, where r is which component does v, the direction over which on which we projected, comes from. Okay? So I don't know if I have to remind you that asymptotically, two sequences are asymptotically equivalent if an and bn, if the ratio between an and bn goes to 1 and then goes to infinity. Okay, so this is this notation. Okay, so this means that this decomposition into k components gives us different order of magnitudes in n for the different projection of the random profile, depending on which direction does which component does the direction on which we project comes from.
Is that surprising, or you would expect it?
I heard two different opinions on that question, so I don't know.
Can we have a small example like k equals 3 of what these spaces look like?
Yes, of course. I think that this is also what, yes, let's do that. Okay, so let's just do what you Okay, take k equals 3. We need to decompose the 6-dimensional space into 3 components, a direct sum of 3 subspaces. So let me first tell you what they turn out to be. If k is equal to 3, then we have r equals 0, and then v0 turns out to be the span of the all one vector. And this is always the case for v0. So it's a one-dimensional space, and if you project on this direction, we already have seen that the order of magnitude of what you get is constant, because actually we've seen that you always get the constant one. It has a constant order of magnitude, n to the 0, which what we expect here, we write n to the r, n to the 0, so it's a constant. If r is equal to 1, then r equal to 2, then v1 is some space, well, I'll not describe, I'll say it is a 4-dimensional subspace from the previous result. So here we know that if we multiply by the square root of n, we have so in this order of magnitude, we have something that is supported on a k minus 1 squared. In our case, it's 4-dimensional subspace. So we'll have something that is 4-dimensional, and the limit distribution is 4 normal 1. Okay, and in this space, indeed, the order of magnitude of the profile is 1 over square root of n. So let me tell you the third one. So v2 turns out to be the span of this vector 1 minus 1 minus 1 1 1 minus 1, which is the sign of the permutation, the sign of the pattern 1 2 3 1 3 2 and so on. And this is also one-dimensional, and the order of magnitude of the projection along this direction is 1 over n, right? Because here we have r equal to 2, and so the square is order of magnitude of n to the 2. It means that this projection has typical order of magnitude of 1 over n. And this is known as Gepner statistics that Doron showed me, and also it was considered by a statistician. So it appeared also in the Fisher and Lee test for some kind of a correlation between two samples that are taken from circular space. So never mind about the detail, but you can see that this component, where the order of magnitude is smaller, 1 over n, sometimes are useful for some purposes, as in Gepner's case, as in the case of Fisher and Lee test, and there are more examples for that. So that means that indeed it is interesting to look at the other direction, where the profile has a smaller order of magnitude than in the first one. Okay. So any questions about the example? Okay. Okay. So before I tell you what the decomposition is in general, perhaps let me tell you about some other properties of it. So you could ask, okay, so this decomposition, I'm telling you that it exists. Is it unique? Maybe you have several different decompositions with the same properties. So it turns out that it is unique under some additional conditions. So one answer for this question is to also require orthogonality. So if you want the decomposition to have this, to satisfy this property, and to be direct, to give us the whole space as an orthogonal direct sum of subspaces, then it is a unique decomposition that has this property. So this is one answer, but I can give you another independent answer. So this is the only decomposition that gives you components that are asymptotically uncorrelated. Okay? And again, this defines it uniquely, but let me explain what I mean by asymptotically uncorrelated. You can imagine that you project over on two different directions, V from VR and U from Vx. R is different than S. So we have the projection of the profile along V and the projection along U. Now we already know how to normalize these components, right? Because we already know that this one will have order of magnitude of 1 over n to the r over 2, so we can multiply here with n to the r over 2 to get a constant order of magnitude, and here we can multiply the n to the s over 2. Okay, so now we have these two random variables. And we want to know if they are correlated or not. So we take the covariance. So the covariance is the expected value of the product. And now this is some number. It depends on, of course, on the choice of V and U, and it depends on n. And in general, it's not 0. But the point is that asymptotically, as n goes to infinity, it does go to 0. And this is a property of this decomposition of VR and VS. It gives us k components that are asymptotically uncorrelated in this sense. Okay, so that's a second answer about the choice of the decomposition and why it is natural.
Is it related to the fact that the number of inversions and the major index are symptotically uncorrelated?
I don't know. I mean, can you interpret the major index in terms of pattern counts?
Yeah, maybe possibly, I don't know.
Okay, then you have to see. So the number of inversion is certainly from V1.
Yeah.
The major index, I don't know. I suspect it's
Yeah,
also
yeah,
from
yeah.
V1. I
Maybe
suspect.
not, yeah.
Yeah. So,
Okay.
but still, this is the same kind of a statement, the same kind of a question. I mean, we have two permutation statistics, and there may be a correlation, but we want them to go to 0 as the n goes to. Yeah. So, okay. So now maybe it's the time to speak about the decomposition. So there are different ways to look at the decomposition, and one of them, I mean, it comes from a representation of the symmetric group. So yeah, so here I'm going to, for a moment, I'm going to assume some background from representation. So yeah, apologize for that. If somebody haven't seen it before, so, but I'm not going to say much. So I'm not going to tell you that from the representation of SK, and maybe I should say from the linear, real, simple representation of Sk, you can somehow, doesn't matter exactly how at this moment, define some basis of the space. So they are called matrix elements, and they are actually vectors. So it's a kind of a Fourier basis of our space, R to the k factorial. And these are vectors that are called Rij lambda. They are indexed by a partition and two numbers, where lambda is a partition of k, and I and j are between 1 and d lambda, where d lambda is some function of lambda. Actually, it's the Hooke length formula of lambda. Okay, so, and together there are k factorial of them, so it's some choice of a basis of this space that appears naturally in representation theory. So why are they called matrix elements? Because actually you can look at them as matrices, and then Rij lambda will give you the ij entry of the matrix R lambda. So R lambda sigma for each sigma, so now it's a number, not a vector, and now it's a matrix, so it's actually a matrix d lambda by d lambda. So, okay, so this is only to explain why they are called matrix elements. Okay, so a partition, so you know partitions, right? So it means that we have a non-increasing sequence of numbers, such that the sum of them is equal to k. So this is a partition of k. What else? Okay, yeah, an important point. So actually, these are not uniquely defined. They are defined up to something. You can conjugate these matrices by something. I mean, as long as you conjugate all of them by the same transformation. So, but this choice is not going to be important for us today. So for any, what we're going to say is going to be right for any choice of this Fourier basis. So maybe in the abelian world where used to a unique Fourier basis is not the case. Okay. So this is the unexplained part. But now, given that, let's define the decomposition. And then maybe we'll see an example. So finally, we define VR to be the span of all those matrix elements Rij lambda, such that lambda is a partition of k. Lambda 1, the first part of the partition. If you think about them as Ferrarian diagrams, the first row is of length k minus r, and any I and j are between 1 and lambda as usual. Okay? So we classify the matrix elements according to the length of the first row. Okay? So for example, let's do the example k equal to 4. We have 5 partitions, so lambda can be either 4 or 3, 1 or 2, 2 or 2, 1, 1 or 1, 1, 1. And the d lambda turns out are 1, 3, 2, 3, and 1. Okay? And now now we have to classify them into R components. So this partition is going to contribute to V0 because the first row is of length 4, K minus R, 4 minus 0. This component starts with 3, so it contributes to V1. The two partitions that start with 2 contribute to V2, and this one is going to contribute to V3. And we can also see the dimension. So this is 1-dimensional. This one is going to be 9-dimensional. 3 squared, I and j run from 1 to 3. This one is going to be 13-dimensional, 2 squared plus 3 squared, and this one is going to be 1-dimensional. And the claim of the theorem is that along this component, we have a constant order of magnitude for the projection of the profile. In this component, it's 1 over square root of n. In this component, it's 1 over n. And in this component, it's 1 over n, which is 3 halves. Okay, so this is how it looks. Okay, so now let's see what's the time. Yeah, maybe I would like to give you another characterization of this decomposition if you don't like this one, if you don't want to go to representation theory.
I like it.
Yeah, but it's going to be similar. So let's see which blackboard. Oh, yes, covers it. Let's get rid of this one.
So you cannot break it up, V2 and V further, to versus separate?
So in terms of order of magnitude, this is the decomposition.
But if you have more refined asymptotics, maybe it's...
Yeah, so it is indeed the next thing to look into. You can ask, let's take each one of these components, and still we have a multi-dimensional distribution, and let's try to diagonalize it. Let's try to bring it to the form using just a linear transformation so that its covariant matrix is diagonal. And maybe it's nicer. I mean, still, the differences between the directions are going to be constant. Not one that depends on them, but still, yeah. So this is indeed some direction I started to work on, and you can find some partial results in the paper about this work that I uploaded to the archive. But yeah, it gets a little bit complicated. I don't want to go into this right now, but let me just say that the representation theory it looks that the representation theory keeps being useful also for this refined decomposition. Yes. Any more questions? Okay. So let me characterize the decomposition differently. So the symmetric group SL sits as a subgroup in SK, right? So K is a group where you can permute K objects, and if you only permute L of them and keep the others fixed, then you have a subgroup, okay? So this is what I mean by SL, this particular subgroup of SK. And now let me define UL as the span. No, actually, it's already span. All vectors in the K factorial dimensional space, so their index, I mean the coordinates comes from SK, such that for every alpha and beta in SK, the summation over sigma in SL of Now V is a vector. Its coordinates are permutation of size k. So you can look at V of alpha sigma beta. Remember the sigma in SL also sits inside SK. So you just sum entries, you sum some of the entries of V, and you want them, you require them to be a zero. Okay? So this is a subspace of this is the subspace. Let me say subspace of R to the k factorial. It's whatever is orthogonal to what? To whatever vanishes when you sum over not only the subgroup SL, but any translation of it. Translation from alpha, by alpha from the left, and by beta from the right. So it's some kind of cosets of SL, but it's cosets from two sides. So this is whatever is orthogonal to all two-sided cosets of SL inside SK, some set of linear equation. And it turns out, so this is now an exercise. If you already know all the representations theory stuff, that UL plus 1 is equal to UL direct sum with V K minus L. I hope I get the indexes right here, but even if I don't, the point here is that V, the subspace we are interested at, are simply the differences between this sequence of subspaces that, of course, grow as we take larger and larger L. One can see that these subspaces actually grow, and each one includes the previous ones, and what's added is exactly the component of V. Okay, so now here you don't need to know about the representation theory, and it gives you another definition of this decomposition into the right components for the distribution of the random profile. And and let me say that this is actually what this is more or less what we need to know in order to show this main result. So we need to know this definition, and we use both sides of it. So, I mean, this is an equality of subspaces, so there's inclusion in both sides, and both of them basically what we use. But perhaps the connection to representation theory is deeper than that. Okay. So I guess my time is up now, right?
Thank you very much.
Yeah. Okay.
Chaim will be glad to answer questions in private. And we're taking him not to the usual place, but it's called Bistro 70 college.